Okay, so in this lecture we're going to talk about odd and even functions, and this is following on from symmetry. We've already talked about x-axis symmetry, and we've talked about y-axis symmetry. There is one other kind of symmetry, and that's what we call origin symmetry. And origin symmetry is symmetry where we actually can see that if I was to rotate this curve around 180 degrees like so, you'd end up mapping onto itself, so it'd come along onto itself. Another thing you could do is reflect it across the y-axis, then reflect it across the x-axis, and you'll end up with this part. And so the way we test for this is to replace both x with negative x and y with negative y and see if we get the same. Okay, now this function here is f of x equals x cubed. So this is y equals f of x equals x cubed. Now if I replace the x part, what happens? Well, with symmetry for origin symmetry, if we do that, we should get the same equation occurring. Alright, so if we do that in this particular case, let's suppose let's replace x with negative x and y with negative y. In this one here, we'd have negative y equals negative x cubed, which of course is negative x cubed. So both sides by a negative 1 gives me this, and so I end up with the same thing. And so we have origin symmetry. We've already seen that a circle has both x and y axis symmetry, but you can see here that it also has origin symmetry. In actual fact, the circle has all symmetries. Okay, another thing to look at here is if I have this point here, which is x, y, then the point I get down here is negative x, negative y. So for origin symmetry, if the curve contains the point x, y, then it also contains the point negative x, negative y. Alright, so we've so far seen, so this is origin symmetry here. We've seen this is, alright, y-axis symmetry. And of course we've seen that if we have this and this, we have x-axis symmetry. So these are special functions that have these kinds of symmetries. Now, this leads us to what we call odd and even functions. Right, and then when we talk about an even function, then what we're saying is that it will have, in fact, y-axis symmetry. And the way we test it, therefore, is when we take f of negative x, we end up with exactly the same thing. Okay, so when we replace x with negative x, we end up with the same y value, same function value. For an odd function, it has origin symmetry. Right, so it has origin symmetry, and in this case, if I take f of negative x, I end up with negative f of x. Okay, so in other words, if I get the negative of x, then I get the negative y up here. Okay, so you can see that this one here is an odd function. You can see this parabola here is an even function. Okay, now the interesting thing is that if I have a polynomial function and all the exponents are odd, then it will be an odd function. If I have a polynomial in which all the exponents are even, and we'll count 0 as being even, then it will be an even function. If it has a mixture of odd and even exponents, then it will be neither odd or even. Okay, so if we look at an example, all right, let's suppose that we test f of x equals 4x to the 4 minus, say, 3x squared. Right, now you'll notice here that if I replace everything with negative x, I end up with exactly the same result. And so I have origin. It's an even function. And it does have origin symmetry. All right, so that's an even function. And of course, if I have, let's suppose I have f of x equals 4x cubed minus 3x here, then notice that if I have f of negative x, the test is very much the same. Cubed minus 3 by negative x, I end up with negative 4x cubed plus 3x, which of course is equal to the negative of 4x cubed minus 3x, which of course is the negative f of x. And so this would have, this would be an odd function. Okay. All right, so that's how we test for that. Now, the next thing I want to talk about is translations. Notice here that I have y equals x squared, my squaring function. So in other words, this would be f of x equals x squared is my squaring function in functional notation. Right, now if you go down to here, this is going to be, let's see, it says 1, 2, so it looks like we're going down about 3 here. And you'll see that this curve has been dropped down right to here. So this point origin 0, 0 has been gone down to this particular point here. So 1, 2, 3, 4, 5. So each one's 0.5. So it's 3, 3.5, 4. So this point here is 0, negative 4. In actual fact, the equation of this is f of x equals x squared minus 4. So if I have a constant here, all right, then if it's a negative constant, it causes the whole graph to move down vertically. So we have a vertical translation. And if I was to go up, say x squared plus 2, then it would go up to here, and I'd end up with a curve that does this. Now it's exactly the same shape as the original curve, it's just moved up vertically. All right, so when I have f of x plus a k, and k is positive, it goes up. All right, if I have f of x plus k and k is negative, it goes down. So this is just translations up and down the axis. When we come to this one, all right, again we have f of x equals x squared. But now this one here is actually x minus 2 squared. Use it in functional notation. All right, so you'll notice here that negative 2 moves it to the right 2 units. Okay, if I was to do plus 2, then it would move it to this way. So if I had y equals x plus 2 squared, it would move it this way 2 units. All right, so that allows us to generalize that if I have f of, so let's suppose k is positive, if I have f of x plus k, then it is k units to the left. And it's exactly the same curve, it's just translated to the left, that many units. If I have f of x minus k, when k is positive, then it's k units to the right. Okay. All right, so that allows us then to draw exactly the same curve, but really we're just translating each point, all right, k units to the left or k units to the right or k units up or down the x-axis. All right, so if I was to draw then something like, so let's do an example, a quick sketch of it. Then let's suppose we want to graph let's do f of x equals negative x take 1 squared plus 4. All right, so a quick sketch of this. We start with the let's take this as 4. Okay, so it goes 1, 1. It goes 2, 4. Negative 2, 4. So we have our regular parabola, and I'll just do a broken line. So this is y equals x squared. All right, now the next thing we want to do, of course, is we would go down, we'd have a negative in front, so if it was negative x squared, then it would be down like this. So it's y equals negative x squared. All right, now we want to go up 4, so we go 1, so we go 1, 2, 3, 4. So it'll go like this. Oh, sorry, there. Okay. Right, because remember we're going, the point will be 2, 4, and we're dropping the whole point, this whole point, 4 units, or pushing it up, sorry, 4 units from here. Okay. So we end up with this thing. And that one there would be actually y equals x squared, but negative of it, plus 4. But now, of course, we have to move negative 1, which of course will mean moving this way 1 unit. So we move all our points 1 unit this way. And so we end up with my scale's a bit off, but there it is. And this one would be y equals negative x subtract 1 squared plus 4. Okay, so your translations here, and this point here, of course, would be 1, 4 now. Notice it's 1, 4. Okay, the opposite sign to whatever's in here gives me 1, and out here is just the regular, what number it is, and it's 4, and that's 1, 4. But it's the regular parabola, just upside down, inverted, and all the points moved 1 unit to the right and 4 units up. And that's how we do a translation that involves a vertical translation, a horizontal translation. Now, and of course a negative in front, which inverts it across the x-axis, if you like. Now, the other thing, of course, to add complexity would be if I had a 2 in here, and then I would have a 2 would mean that I would stretch it vertically so it would get narrower. Okay. If I had a half, of course, it would get wider. And so you have these kinds of variations. And so it's important that you look at the summary of graphing techniques that every college algebra book has, or pre-calculus book has, and have a look at what the translations are, because these are going to be techniques that will allow you to draw graphs much quicker, right, than having to plot a whole bunch of points and trying to guess what the shape is.